So this presentation is here to give you an overview about the motivations and the history behind this simulator. We also see that there is, as I said, quite a few presentations which are available through the website. So you can also have a look at more specific features of it. So this simulator is trying to talk about distributed systems and most specifically about distributed computer systems. These are in many different communities. We talk about large systems which are heterogeneous, which are dynamic, which are very complex. And so in order to conceive this and in order to design them, it's very tricky. In particular, we want to consider two things. We want to make sure that the system and the application that we design do actually work. So we want to ensure that we have correctness. That's one. And we also want to make sure that it delivers the level of performance that we expect. So if we talk about correction, the first thing we can try is test it. Okay, so you will run a few tests on your application, or a lot of them, and hopefully you guess correctly the use cases, and hopefully you will detect problems. But you will not get a definitive answer whether your system and your application is working correctly or not. There is another way, which is model checking, in which you are going to explore exhaustively all the states. Difficult, this does not scale well, but with a few tricks maybe we can get to something interesting. Then there is another interesting question is whether you will reach the performance that you are looking for. The first thing you can do is look at mathematics and try to do theory around it. But since these systems and these applications are very complicated and very large, very often you will miss some dynamics. And as a consequence, you will not envision everything that is going to happen. Then you could try to actually experiment with the system. But in many cases, the systems will not exist yet, or it will be difficult to access, or it will be expensive to access, etc. So there is a third option, which is simulation, in which you are going to prototype your system or your application, and you are going to run it on a synthetic platform. And then there is, in between, what we call emulation, where you take your actual application, and instead of running it on the actual system, you will run it on a platform, on a model. So pretty much this is what I said. Basically, we want to simulate distributed systems because is not enough often, and actual systems are very difficult to get hands-on. And so it looks very much obvious that other sciences are using computers to simulate their own domains, which should probably use computers to simulate our computing systems. This is an example of applications that we want to look at. Weather change, climate change is very important, and so we want to have models which are more and more performant and more accurate, so that we can understand what happens. And so, as you can see, through time, you see that the models are going to are getting deeper and deeper, and this and they consume more and more energy. And currently, we are trying to design exascale systems, which are indeed very complex and very difficult to understand. So the big idea behind simulating this distributed system is, let's say you have a big idea, and what you would like to do is patch a few things together, do a partial implementation of your big thing, run it, try to maybe run it with significant instances, so maybe they need to be a bit big so that you can see what happens. And then you want to be able to add things more quickly, so that you can get to some good scientific results for those of us who are in the academic world, at least. But a point which is important in Simgrid, and especially to the core developers, is that you want to do that the right way. And in particular, what they are focusing in, and I think more people probably should, is to try to obtain reproducible results. That is, that if someone reads your paper or reads your research, then he should be able rather easily to do the same thing in his lab and then improve on that. Okay, and unfortunately, this is something which is not happening too often, because very often you have short-lived simulators because a guy needed a simulator, so he wrote something very quickly, he did his paper, and then he died. So there is this idea that you should, we would like a framework which is long-lived, which is developed correctly enough so that you can get reproducible results. Another item, and we'll see that in a moment, is that you would like that this simulator is easy enough to take hold of, so that you could have students to play with it in rather easily. This simulator has one of its characteristics is that it's very versatile. So as I said, we could talk about high performance computing, HPC, we could talk about grid computing, we could talk about cloud computing, and now we can also talk a little bit about storage, about VMs, and so on and so on. It's quite well validated, and we'll come back to that in a moment, but they go to great length in this sector at least, to make sure that this simulator is actually delivering what it should. It has been used quite a lot, and this is something that is being developed for now 20 years. I have to stress that these slides date back from 2015, which in many cases is still valid, but in some cases it's a bit obsolete. And so you see that it started in '98 in University of San Diego, and then it got mostly in France, and then it got supported by various research projects. And now you have committers mostly in France, but also in other places, including myself. So this is something that is here for a long time, that has been where a lot of efforts have been given, and it's still very much alive. So if we look a little bit very quickly about what is happening in there, on the user interface you will have three systems, interfaces basically. So you have SimDAG, which allows you to simulate parallel tasks which are exchanging messages between each other. You can use MSG, which allows you to simulate concurrent sequential processes. So you have some mailboxes between the processes, or you can have SMPI, where you can simulate virtually unmodified MPI programs. There is another one which is called S4U, which is not here because this script is a bit old, which is an object-oriented interface, so that you can touch a lot of things in the simulator. The Simgrid framework is also organized in layers, so that you can have a nice isolation between the different functions of it. And typically, so you have MSG, which is, or the others, which are what a normal user will probably be using most of the time. And underneath, you will have Simix, which is going to try to rationalize the task and the communications. And in the very below, you will have the actual model. In this case, what is called LMM. So when we talk about models, and obviously we are talking about network simulation, we want to make sure that, or we should want to make sure that the models that you have are actually representing reality. And but what happened, at least in the beginning of the life of Simgrid, is that in many simulators, the model that was used was not very correct. In some cases, it was actually quite wrong. Instead of that, Simgrid is first trying to validate very much that the models that are being used are actually valid and try to determine what are the boundaries within which they can be used. And it also proposes different models depending on the kind of study that you want to do. In most cases, what you want to look at is a flow-based model, which is modeling nicely Ethernet-based applications and a little bit more. So I'm not sure we want to go too much into the math, but just let's say that you have flows of data between different hosts, and you want to model the time that it's going to take for message to reach its destination. And basically, it comes back to solving an optimization problem. And what Simgrid does at its core is that it's solving this problem very efficiently and very scalably. So this is an example, and basically what you want to do is that if you have two flows sharing a link, you want that each flow will take half of it, for instance. So that's the basic idea, and Simgrid does it a lot of time. I should stress that there are other models which are more simplistic, which are delay-based, which means that if you have a message is going through a given set of links, the delay will be constant, regardless of how busy they are. So it's an approximation. In some cases, it's valid, but not always. But other simulators do use this, and it's not always the best option. So these are two examples of cases where the simulator typically you would expect that this output, so that the restricting link will reduce all of its capacity, but in practice you have a big mishap here. And in another case, the simulator will just model a bigger capacity than what you expect. So which are two mishaps that they actually saw in actual network simulators. What is done in Simgrid for this flow-based model is something more fancy. So basically, you want to model the fact that depending on the message sizes, you will have different latency because the mechanism that you use at its core is different. And so you have this segmented curve that is being modeled inside of Simgrid. So once you get these characteristics, and they are pretty standard for Ethernet in the Ethernet world, then you know that, for instance, you have this kind of hierarchical system. Okay, so you have concentration here. Then you are going to model it into a platform. So you are going to write an XML file for this, and you are going to describe this architecture. And then it gets to work. So in this case, what they did is that they took an MPI application, they wrote the platform file, they run it in the actual system using OpenMPI, and they run it on the simulator. So what you are looking at is for each of the cores, what it's doing at the given time. So typically in blue, it's computing, you have some barriers in red, etc., etc. And we see that more or less from far, the pattern is correct. And also you see that the completion time is quite close. So that's a good thing. In some cases, even, you would see that the simulator is going to give you a number. The reality is going to disagree with this number. And when you look at the bottom of it, you will see that actually the reality should be fixed. And this is such a case where the network was getting very congested. And so you were starting to have a lot of, you have TCP which reduces emissions. And as a consequence, you have a lot of timeouts here and there. And so your time span is going to increase a lot compared to what it should. So it means in some cases, allows you to detect some problems with reality. And this was also the case in one of our very own studies. So, how do you reach scalability and also achieve versatility? Well, there are a lot of different ingredients for that. One of them is that you can take advantage of the hierarchy, the inherent hierarchy of your systems. Typically, in Simgrid, you can define your platform, and you can put a lot of details in places where you think matter, and in other places you can be a lot more approximated. Okay, so this allows you to go quite far. There are other techniques which relate more to the computation side, which I'm very happy to discuss afterwards. But yeah, in general, the idea is that you can generate big runs quite easily. So, how big? Well, what they did is that they compared to the state of the art in terms of simulation. The first set, because it's the original community of Simgrid, was for grid computing. And what they did is that they compared it to GridSim, which is using a delay-based model, so something which is more simplistic. And they saw that Simgrid was faster, used less footprint, so that was a good thing. Then they looked at peer-to-peer, where you have obviously a lot of hosts communicating together in a rather sparse way. And they get up to 2 million nodes, whereas the competition per se.
Could you please move to the back? I don't see the
Sorry.
slides.
Whether the competition has to stop 1 or 2 orders of magnitude before. Okay, so we are again, Simgrid is a bit faster there. And then there is HPC, in which case, again, if you compare to more simplistic models like log-gopsim, which use delay-based modeling, well, we get a bit slower, but we get realistic. So that's a good thing, again. So now you have your system. You were able to create the platform, you were able to run it. Then the question is, how do you get result from that? How do you visualize what you have? And so Simgrid, as it is not going to provide you simulation tools, visualization tools, because it proved difficult to have a tool which is going to encompass all the different use cases that you could have. Instead, what it does is that it's going to provide you a tracing mechanism which is very flexible, so that you can generate exactly the right kind of traces that you want, and then it is going to point you to different tools that are going to give you a different visualization. I wanted to prepare something, I didn't get the time, but we can have a look at it if you are interested. And a small item that is very dear to these people, if you remember in the beginning of the talk, I was talking about model checking as opposed to testing. What they did is that they implemented this in Simgrid, which means you could have your MPA application, you could use model checking on your MPA application and make sure that in all cases it will be successful. Of course, you will have to limit the size of your instance, but it was able to find quite a few bugs and quite a few limitations in existing systems. So finally, I would like to talk a bit about the trust in Simgrid. So as I said, this is a simulation framework which is now almost 20 years old, is still very much alive. There is regression testing, continuous integration, meaning that you have a Jenkins server running every night and trying to make sure that the latest commits are running on many different kind of platforms. So that gives you some good confidence that it's actually doing good things, or at least in this domain. Of course, it's free open source, and the community is very open to people who want to contribute. So, to conclude this introduction, this is something very versatile. You can use it in many different communities. It's quite accurate, again, because people will check that the model that you are using is actually sufficient, is actually good enough for your study. And you have different models depending on what you want to do. It's quite sound, I would say, and it should be easy to use. We'll see in a minute. And last but not least, it's open. Okay. So that's the end of the talk. What I would like to us to do now is to try to play a bit with this simulator. So I'm not sure exactly what are the interests of everybody. I have a small course or a small topic which is taken directly from the Simgrid material, but maybe we can, if you have some questions now, I can answer them and then we see what we're interested in.
I have a question because I'm a little bit unfamiliar with the whole concept of the simulators and I'm a little bit confused. For example, let's say you have a network of 15 remote nodes.
Okay.
When you want to use the simulator and you want to verify that the results will be the same with the actual network.
Yes.
So you run the simulator on only one machine.
Yes.
And you describe the hardware of what it would be.
Yes.
Okay.
Yes. So typically, what you could do, let's say that if you go back. Okay, let's say that this is what you want to model. So let's say this is a cluster with a lot of nodes, all right, connected together. So you will be on your machine and you're going to write this platform file, okay? And you're going to say that, okay, I want, typically what you are going to do is that, okay, these guys here is a cluster. So they are connected together and they have a bandwidth between them of 10 gigabit, for instance. Then you say that you have a link to the top and then there is a latency of this much on each link, all right? So you are going to describe this platform. You're going to say how much each host has in terms of core, in terms of performance per core, etc. So you're going to describe this. It's a bit rough in some cases, but it should be enough for most of the studies. And once you have this platform, you are on your computer, you run this, it will run on your computer only, and it will give you some results. Obviously, if you want to run very big applications, which should run on a big HPC system, and you run it on only your PC, it will take a lot more time, right? So you will have some limitation. But again, in general, it's enough so that you can have some ideas about it. And if you are willing to spend a little bit of time, you can approximate a few things and focus only on the things that are important for you. And then you will be able to have a decent idea of what is going to happen in the actual system using only your own PC. I would like to stress that this is a nice feature, for instance, if you want to, for education, if you want to teach people distributed systems, each one can have its own PC and simulate a few things.
Can it simulate a network partition or things like that? So if I have a component but that's on the network,
yes.
Can I test different cases for the network? Like the throughput, like error rate, bandwidth, network breaking.
Yes, definitely. So the first thing is you could have different platforms, okay, and you can try if it's about varying the latency of links or the throughput of links, you can have different platforms and see what is the time span depending on the platform. If you are interested in the reliability of it, there is also the possibility to shut down some links, and you will see some transfer failing. So this you can model. There are a few other things that are interesting. You can talk about energy, so you can try to model the energy consumed by your application. You can talk about storage again. There are a few more things that are not here, but you can look at.
And one more question. Somewhere at the beginning, you said the concurrent sequential processes.
Yes. No. Yes.
Okay, so from current or sequential?
Yes, it means that you have. Those are not my slides, but I very much think that the idea is that you have different processes running sequentially on one host, and but you have different hosts, so they run in parallel. All right. So you have different.
Because if it's a model that I think it's called communicating sequential processes.
Yeah, I would think so, because then you have mailbox between them, so that must be communicating. Yes. Yes, correct.